Hello, this is Dr. Muhammad, and this is the Dynamics of Structure course. So I'm going to talk today about an introduction about the course, and already I have mentioned before about the table of contents or the contents of this course. So I hope that we can go smoothly for the contents that already we have addressed before. Now let's jump directly to the main contents that we are going to have for today's lecture. So first of all, I'm going to touch upon 5 main points, as you can see here. The first one is related to the objective of structural dynamic analysis, and we are going to talk about what is the main objective of dynamic analysis in general for us as engineers. And after that, I'm going to talk about the types of dynamic loading. What is the different types of dynamic loading that we are encountering in our daily life. And after that, I'm going to talk about the dynamic problem versus static problem. I'm going to address what are the main differences between static and dynamic problems. And after that, I'm going to give very important and basic definitions related to structure dynamics. I'm going to talk about important things like mass, damping, and stiffness, and so on, which is commonly going to be used during our class. And after that, I'm going to talk about the components of basic dynamic system. What are the basic components of any dynamic system? Okay, now let's go to the next slide, which is going to be about the objective of structural dynamic analysis, as I have mentioned. Okay, now first of all, whenever that we are talking about dynamic or dynamic analysis in general, the word dynamic in itself means that time varying. So this means that we are having one axis, which is going to be the time, which is the horizontal axis, and we have the vertical axis. We are going to find it as the component that we are interested in, which might be acceleration or deformation or forces or stresses. So whatever the type is, we are going to put it in the vertical axis. This means that our dynamic system is not described by or at a particular point in time. Rather, it is or it should be described as you can see here, with the different at different times, at different points of times, and it should be described along a history of time. So we have like a specified particular time that we need to describe our problem or our system in. Okay, so this is what we call it, time varying, and this is the meaning of dynamic whenever we hear the word dynamic. Okay, the objective of dynamic analysis in general for us is to obtain the structural responses. So we need to know the structural output responses. Commonly for us, we need to know about displacement, forces, and stresses. So if we are going to talk, for example, let us assume that we have a building and there is a time-varying time history, ground motion is going to strike this building. Okay. The point is, what we are interested in, this building, which is our system, this time history record, ground motion profile is going to strike this system. We want to know how this building is going to deform under this ground excitation. What is the maximum deformation that is going to take place? What is the maximum ground acceleration underneath this building, which is going to be described by our the ground acceleration, and how this acceleration is going to be augmented or magnified at every level of the system, and what is the velocity at each level of this system. Okay, so this is what we are interested in. So we want to know some issues related to our system. Okay, this is the displacement. From the displacement we can obtain many things, and one of the major things that we can obtain, which is related to the forces. So if we know how much delta or displacements are going to take place under the earthquake or under this dynamic loading, then we are going to find a way to get the forces in members. So for each column and member, if we have, this is the columns for example, this is the beams, then under this delta we are going to obtain what is the forces that is going to take place in this beam. This is number one. And after that we can get, if we are interested in other type of forces, for example, this is maybe bending moment, we are going to find also the axial forces in this column, and we may be interested in the shear forces in the beams. So they are going to be obtained based on the first thing, which is displacement. After that we are going to obtain the stresses. So at the end of the day we're going to say the force at the end of the beam is, let's assume, 100 kilonewton, for example, shear, or this is if it's shear, or if we're talking about bending moment. In this case, this forces is going to interpret it into stresses. So it is going to be, if we are talking about moment, for example, my over I, this would give us the stresses in the element under consideration, whether it is a beam or a column or whatever. Okay, so actually this is what we wanted, or what we want to highlight here. Okay, so let's okay, so I think that I'm going to use this pointer. I think it might be better for us. Okay, so now we are understanding what is the meaning of the structural response that is needed for our system, and based on it we can say that this is our main objective. Okay, now we understand what is the meaning of dynamic loading, what is the meaning, or what is the objective of the solution of this dynamic loading and obtaining the structural responses. Now let's jump to another thing and see now how to obtain structural responses. Actually, we can obtain structural responses by extending the structural analysis of statics to deal with dynamic loading. This is the philosophy that we are going to follow. We are going to extend. What is the meaning of extend or extending here? This means that there is something already well established, and we are going to extend it to deal with our own problem. So extension, or the extending, by extending the structural analysis of what? Yes, statics. So statics already we have like studied before in different classes, and we are able to get and obtain the displacements, stresses, forces at a particular point of time. But now, as the problem is dynamic, we need to solve this or obtain the structural responses at different point of times. As I said, that we have like different point of times, and we have the force here or whatever that we are describing. This means that we want to solve static problem here, and another one here, and another one here, and so on and so forth, so that at every time we are going to get or obtain our results. So we are going by some way, as we are going to study during this course, we're going to extend the analysis of statics to deal with dynamic loading, and we are going to find that it deals with two different types, or at least we can deal with this problem into two different ways, or by using two different ways. One way is deterministic way, and the other one, it is non-deterministic. Sorry, here it should be non-deterministic. Okay, so it is deterministic or non-deterministic. What is the meaning of this? The meaning that we have two approaches. If our time variation, which is the input loading, time variation of loading is fully known, if we know the input loading, if we know exactly what is the input, if we're talking about the system, and we know exactly what is the time history of the input, then we can go to the deterministic approach, and then this would lead to, or this approach leads to displacement time history. So we are going to say, if we are interested in the displacement at the roof at this point, then we can say that the displacement of the roof at different times, it will be something like this also. So we know the input, we can obtain the output deterministically, because this is known for us. Okay, the input, ground motion time history, or time variation of loading is fully known for us. But what will happen if that we do not know? We do not know the loading, how we are going to work, or how we can deal with this problem. Actually, if we are having random dynamic loading, random dynamic loading. So random dynamic loading means that we are going to, random dynamic loading means that we are not having the full, or we are not knowing exactly what is the time variation of the loading. Okay, so it's a kind of random for us. It is a kind of random. Okay, so this means that we are in a position where that we do not know the input. This would provide for us, it provides statistical solution for displacement. So we are not going to have the deterministic output. We're not going to have the deterministic output. We are going to have the statistical solution in this case. Okay, so if we are fully knowing the time variation of loading, then we are going to obtain deterministic output. But if it's random, then we are using non-deterministic, and it would provide statistical solution. Okay, so this is from the perspective of the divisions and categories of the solutions. So if we are saying that this is the solution, for example, it has two different categories. But how we can process the solution itself, how we can process it. So the process flow of whatever deterministic or non-deterministic, it is going to deal with three different steps. So we have like three different steps that is usually and commonly we are going to follow in all of our problem solving for most of our problems. We are going to follow these three steps process. The first thing is we are going to understand will and describe the motion. So we need to describe the motion. Describing means that you need to understand how the motion is. What is the type of motion exactly? At which degree of freedom, for example, or at which direction? And what is the input loading history is. So this is by understanding the motion itself, how the structure or how the system is going to respond to this motion, and how we can figure and configure it out. This is the first step. The second step is, after understanding and describing the motion, we are going to pick the physical law. Pick the physical law, which is going to follow Newton's second law, for example, or the first law, or whatever that physical law that going to fit to our motion that has been described in step 1. And then the last step is going to be that is how to like transfer what we have understood physically to be understood mathematically. So we are going to apply what we call it math or mathematics. So we have like a physical law that is going to give us a kind of equation, for example. This equation is going to be needs to be solved. So we're going to apply our math skills or mathematics skills in order to solve and find solution for the motion that we have already described. Okay, so this is considered to be, in this slide we have discussed about what are the types of the solution, whether it is deterministic or non-deterministic, and what is the process flow in order to obtain the solution. Okay, now let's go to the next part of our lecture, which is related to the types of dynamic loading. So we're going to talk here about the types of dynamic loading. So we have, let's go to the next slide. So we have here like two main types of dynamic loading. We have type 1 and type 2. So in type 1 we call it periodic dynamic loading. Periodic dynamic loading. This means that the loading is repeated in a certain form. So periodic means that it is repeated. So we have like different types of periodic loading. We have sinusoidal, which is simple harmonic, as you can see. This is the loading that is the loading profile, and simple harmonic means that it can be described by sine and cosine. This is number 1. Number 2, we have, or the second type of periodic dynamic loading is triangular loading. We have like this way, which is triangular loading for the system or for the input loading. And then there is another type, which is the complex form, which is, as you can see here, it is repeated, but it is like complex. It is not like sinusoidal and not triangle. Okay, so we have like different way. Actually here, this and this is, you can find it in machinery. For example, if you have machinery equipment and you have an equipment here, for example, whenever that you turn on this equipment, it is going to provide like different types of harmonic or maybe sinusoidal or triangular or something like this for the structure that is being supported by. But for this complex system, it is actually this complex, we can find it, for example, for the propeller of, like, do you know the big vessels and ships and so on? They have like kind of propeller here. This propeller, the signal of loading that is coming out of it is similar to this complex form. Okay, so this is the periodic, which is repeated. Okay, other types, which is non-periodic dynamic loading, and the most famous two types of non-periodic dynamic loading is the earthquake, which is going to be one of the things that we are going to explain in detail in this class also, and we are going to talk about it in some details, because there is a relation, actually important relation, between the earthquake excitations and the dynamic analysis. And then we are going to give some some hints about how dynamic analysis can serve the earthquake in general. Anyway, for earthquake, it is considered to be non-periodic dynamic loading, and in this case we are having like long duration. We have a long duration. This long duration means that we have the the horizontal axis, which is described by time, and the vertical axis is considered to be, or describing the amplitude, for example, of this earthquake. And then we have this kind of profile of the signal, as you can see it here. So this takes like long time, so in seconds, maybe 4 seconds, maybe more than this, okay? But in pulse loading, which is the second type, if we say this is A, for example, and this is B, for pulse loading, it is short duration impulsive loading, and as you can see here, it is in a very short time it goes high. This is the impulse loading here, and then it goes down, and maybe it goes in the opposite direction for a very short time and then goes back again. So this is the short duration impulsive loading. Okay, so now we know about, at least that we know that there are two different types of periodic loading, of dynamic loading, which is non-periodic or periodic. Okay, now let's jump to another slide and see what we are going to see here. So it is, now we are going to talk about the dynamic problem versus static problem. So we're going to talk about dynamic problem versus static problem. So whenever we talk about the dynamic versus static problem, we need to understand the major differences between them so that we can differentiate well between the two. So number one, and which is already I was talking about, is the variation with time. Okay, so in general, whenever we're talking about dynamic loading in general, or dynamics, or structure and dynamics, it is time consuming and complex, because we need to describe the solution at each time. So we need to consume a lot of time for the solution, and the solution is involving differential equations and a lot of math. This makes it a little bit complicated compared to the static one. Okay, so this is the first difference. The second is going to be that we need the solution at each time step. As we said, if we have this output, okay, if we have this input for the loading, then the output should be described also. This is maybe the displacement with time. Okay, so this means that we are going to describe the problem in different at different times. Okay, the next one is, or the second major difference is the inertia forces. So we understood now the first one, now this is the second one, which is the inertia forces. What is the meaning of this? The inertia forces is one of the major differences between static and dynamic. In static analysis, because we are applying the load slowly, so if we have a beam, for example, okay, and this beam we are going to apply force here. Okay, this force is going to be applied slowly. Okay, statically, we are going to put this load to be like in a very there is no rate of application of this loading. This means that we are here in static condition. Okay, we are in static condition. What is the meaning of static condition? The load, there is no rate of this load, or the time of applying this load is so short, and there is no time rate effect of this loading. It's not dynamic, it's static. So we call this as static condition. In a static condition, this means that there is no acceleration. There is no acceleration is going to take place. For this particle, for example, there is no acceleration. It is going to deform in a way that is not taking or without any accelerations. This means that our system is going to be in a static condition, okay? And in this case, equilibrium will be due to external force only. So we have external force being applied in the system, and the system is going to have some straining actions, and these straining actions will counteract the application of the external loading, right? So this is what we have here. Remember, acceleration in the static condition is equal to 0. But what if that we are having same case, but with the application of load is varying with time? It is P of t. This means that the system is going to respond to this external loading with some inertia forces. This is what we call it the dynamic condition. This is going to be the dynamic condition. And the acceleration A in this case will not equal to 0, right? It doesn't equal to 0. The acceleration doesn't equal to 0. Okay. In this case, this is what we call it the dynamic condition. And in this case, equilibrium is going to be due to two things here: external forces, or external force, and inertia forces. So we have two different components. Here, in the static condition, it was only external forces only. There is no type of inertia forces, or no inertia forces going to be developed here. But here, in this system, there is inertia forces going to be developed. So we have two main components that we need to take into consideration. Okay? So this is the case here. And what is the inertia forces here that we are going to have? If we say the external force is going to be P of t, and in this case the inertia forces that is going to be developed based on Newton's second law, okay, then this inertia force is going to equal minus m, the mass of the system, times the acceleration that is going to be developed, right? So this is what we call it the inertia force that we are going to have, if inertia, for example, okay? So this is the main difference between the two systems, okay? One thing is the variation with time, the second thing is the inertia forces that we are having, okay? Now let's go and have an exposure to the meaning of the Newton's first law and Newton's second law, okay? So in short, if we want to mention about the Newton's first law, we can say that an object at rest remains at rest. An object in motion remains in motion at a constant speed and in a straight line constant velocity unless acted upon by an unbalanced force. So this is the main thing, or the keywords that we need to highlight here with this illustration here. So if you are going to, the object is going to be at rest, or if it's at rest, then it remains at rest. And if it is under motion, it remains in motion at a constant speed, okay, as long as there is no, or unless that it is acted upon by an unbalanced force, okay? So we have here, we can like interpret it by this. We say that the forces are balanced. In this case, the objects, whether they are in rest or the objects, they are in motion. And rest means that velocity equal to 0. And if it is in motion, this means that velocity does not equal to 0. Here, the acceleration equal to 0. Here, acceleration also equal to 0. Remember that acceleration in this case, it is 0. In this case, the system would remain at rest. And if it is moving with velocity, it stays in motion. Same speed and direction. Okay? So this is what we need to know. Forces are balanced. if we're going to talk here, forces are balanced, resultant forces, which is the summation of forces in the system. Okay, the acceleration here, it equals to 0. So whether that the system would be at rest, means that the velocity is 0, so it stays at rest, or the system is in motion, so the velocity does not equal to 0 and stay in motion. Okay, this is simple. I know well that you know about this Newton's first law, but I just want to remind you with it. And the second, which is important for us, is the Newton's second law, and simply we can give this definition for it. Newton's second law of motion states that the rate, take care of this word, rate of change of momentum of a body is directly proportional to the applied force. Okay, according to Newton's first law of motion, if no net force is acting on a body at rest, then the body remains at rest, or if the body is moving, will continue to move. But here in the second law, as we said, it is important. The rate of change of momentum. Momentum means that m times v. M times v. Mass times velocity. For example, if you can look to this Newton's second law, if we have here a car, okay, at certain position x node and at certain point of time t node, and after a while it moves to another position after a time t1, then it has velocity here v node and m node, and here it has v1 and m1. The force is going to be the change of momentum with change of time. So the difference form is going to be f m1 v1 minus m node v node, the momentum here, or mv here minus mv in the initial condition. And then if we assume that m node and m1 are the same because it is the same mass, then the f is going to equal m as a constant times v1 minus v node over t1 minus t node. This is the difference in time. This is the difference in velocity. And then we can say the force equals to mass times the acceleration. Okay, mass times acceleration. So that's the meaning of Newton's second law. And this is something that illustration for you. If you apply more force to an object, it accelerates at a higher rate. If we put the force here, and this is the mass, then there is acceleration. If you put more force, you're going to find the mass is moving with more acceleration. Okay, here the speed here is increases, and here the speed increases faster. Okay, now this is the first law and second law of motion. Why I'm talking about this first law and second law? Remember that we want to highlight the dynamic problem versus the static one. So this is why we mentioned about the two main differences, okay? And the second one is related to the inertia force. Whenever we mention about inertia force, we need to mention about Newton first law and Newton second law, okay? Okay, now let's go to the next slide, which is related to basic definition related to structural dynamics. Basic definition related to structural dynamics. Okay, I'm going to give some definitions here related to the structural dynamics. It's going to be very important for all of us to know them. So let's start with the vibration. What is the meaning of vibration? I'm going to write some definitions here. I hope that it will be good for us to know it. We can say it is a time-dependent displacement of a particle or system. So we're talking about particle or system, whatever the type that we are going to deal with respect to its equilibrium position. Okay, this definition is important actually for the vibration. It's a time-dependent displacement of a particle or system with respect to its equilibrium position. Okay, now let's understand more if we are going to give another definition, important definition, which we call it period. Okay, and the designation is going to be T. So in period, we can say it equals to, if we have like a relation between the horizontal and vertical axis, the horizontal axis is going to be T, and the vertical, it is going to be Y, if we say that this is the displacement, for example. Okay, so in this case, we are going to have like a relation here, something like this. The distance between, or the time between this point here and having a complete cycle, we call it T. Okay, so we call it T. It is the required time. We can define it as the required time for a motion, to be repeated. Okay, so this is the meaning here. It is the required time for a motion to be repeated. Okay, so this is the vibration and this is the period. So this is important to definitions now. Let's go to another definition here, which is related to the circular. Maybe I can, like, before this we want to give something for it. So here, okay, so the circular, let's go to the circular frequency of a system. This circular frequency, let me check here something. Okay, so we are going to have the next part, which is related to the, sorry here, let's use this. So we're going to have another definition, which is going to be the frequency. This is going to be the frequency, which is going to be, we call it F. And this frequency, it is going to be the number of cycles per unit, of cycles per unit time. Per unit time. So we call it that F equals, or we can put it like this, 1 over T, which is cycles per second, and this is what we call it Hertz. Okay, so this is the main equation that is describing our frequency, which is, the definition is the number of cycles per unit time, the number of cycles per unit time. Okay, and then the cycle, what is the meaning of cycle here, the definition of cycle? It is a complete motion during T. Motion during T. Okay, or the time, I mean that, sorry, this is, we should put it like T. So it is, wow, sorry for this. So I think that okay, so this is, again, I'm going to write it again, which is 1 over t. This is the frequency in cycles per second. And the cycle, or cycle itself, it is the complete time, which is, if we are going to describe it, so it is the complete time if we have something like this, t here, and any function, for example, or f here or something, so, or y of t here, then this is the complete, the cycle, this is the cycle, which is during the time t, it is, we call it the cycle. So this is the cycle, which is a complete motion during t, complete motion during t. And then the last thing is going to be the circular angular frequency, which is going to be here, the circular angular frequency. We call it omega. It is, we call it omega. So actually this circular angular frequency, it's supposedly equal to, omega equals to 2 pi over t, and it should be in rad per second, rad per second, okay? And we can say that is, this is the definition of it, and it is going to be defined as the angular, if we put it in equation, it is going to be, says like this, that is angular displacement theta over t, okay, equals to theta over t, where this theta, it is the angular displacement, and t, it is the time interval. To understand these two parameters well, we can look to this relation here between x and y. If we say that we have a circle, okay, the location where that particle point, which is like the dark donut here, or this dark dot here, position at time ti, then with circular angular frequency, it is going to be in a position with time t final equal ti plus delta t, and the difference between the two, from the angle between the two, is going to be theta, okay? So this theta, or delta theta, if we're talking between two different positions, is going to define our angular displacement. So actually this theta or omega, whenever we say that it equals theta over t, it is like the linear velocity. And in linear velocity, we say that we have like distance over time, right? So here this is for linear velocity. But for angular velocity, instead of having this linear distance, okay, we are talking about angular distance, which is theta, can be covered by theta. Okay, so this is the definition of circular angular frequency. Now let's go to another important thing, which is giving to us the description of an important definition here, which we are going to call it harmonic motion. Harmonic motion. This is an important for us to know. Okay, in the harmonic motion, we say that, as we said before, it can be described by sine or cosine. So this is the meaning of harmonic motion. It means that it can be described by sine or cosine functions. So this is the meaning of the harmonic motion. Actually, most of the engineering structures, they are responding, and free vibration of engineering structure is harmonic. Okay, so most of them. So harmonic means, if you want to put the meaning of harmonic, so harmonic means that the problem can be mathematically expressed in terms of sine or cosine. Okay, so the harmonic motion means that the problem can be described in sine or cosine. That's the meaning of harmonic. That's the meaning of harmonic. Okay, again, so the harmonic means that the problem can be mathematically expressed in sine or cosine, okay, function. And we can find, if you remember, I want to highlight something important. That is, sometimes we have, as I said before, we have like complex functions, which is something like this. Right? This is, we call it, it's repeated, and we said another type, which is the triangular load, right? And we have something else, which is like the other one that we were talking about, which is sinusoidal. So what is the difference between this sinusoidal and the periodic that we have mentioned before? So in this is, we call this periodic, right? We call this periodic. And in the periodic, it is going to be repeated with time. So repeated every t with the same pattern of loading. So repeated every t with the same pattern of loading. So here the same pattern is going to be followed again. Okay? So every t, this is t for example, then it is going to be repeated again here. Okay? And so on and so forth. This is what we call it periodic. Okay? But when we are talking about harmonic, okay? In harmonic, it can be described by sine or cosine function. Okay? Sinusoidal function. Okay, what is the difference between the two? I can't put it in this definition. I can't write it for you. So every harmonic loading is periodic, but not all periodic loading is harmonic. Okay, so I can't put it like this. Harmonic loading is periodic. Okay. But not all periodic loading is harmonic. Okay, so this is an important definition for us to understand the difference between the periodic and harmonic. Okay, now let's go to the next part, which is if we have like a circle. So let's go, we can draw it here for example. So if you have a circle here that we are going to use always to describe our harmonic loading, and we have a point here, this is, we call it point P, and it has a projection here on the vertical axis, which is going to be P prime. The vertical axis here, let's assume it's Y, and this horizontal axis is going to be X, for example. The angle here is theta. This point is the origin, which we call it the origin O, and the radius of this circle is R, and this particle, it starts from, for example, from here and moves with a constant angular velocity omega to be, as we have defined it, theta over d, and we are going to assume it to be constant here. We are going to assume that this omega is constant. Okay, this omega is constant. Okay, So first of all, for omega, we are going to define, that is, we have theta, which is the angular displacement, right? And we have theta prime, or theta dot, and it is the angular velocity, right? And we have theta double dot, which is going to be the angular acceleration. Okay? So in the second one, this is what we call it, the angular velocity omega, okay? Which is what we were talking about here. So this is the angular velocity. Okay, that's very nice. And now we want to know more about this. One thing only to know about this projection from here to here. This projection actually, it is, we call it, let's assume it, y equal to r, which is the radius times sine theta, right? That's very true. Because if we are talking about this is the vertical projection of this point on the y-axis. Okay? This means that I can put it only, I'm going to manipulate it, so it is going to be r sine, and instead of theta, I'm going to write like this, theta over t times t. Is there anything here I did, anything that is not logic? Just I put t in the denominator and I multiplied by t, so they are as if they are not here. But look at this, what is this? Theta over t, it is what? Exactly the angular velocity, so we can put it like y, sorry, here equal to r, this is r here, sine, and then here we are going to put omega t, sine omega t. So the horizontal the vertical projection, it is directly equal to r sine theta, and this vertical projection, we are going to manipulate it to find that it would equal to y equal to r sine omega t, r sine omega t. That's a very nice description. What is the meaning of this? The meaning is, whenever this point, which is here on the horizontal axis, is going to move along this circular arc, there is a projection on the vertical axis. We are going to describe this linear motion by using what we have explained here. So I can describe the point, instead of where exactly it is here, I'm going to describe the projection of the point on the vertical axis y. So I'm going to say that this y equal to r sine theta. But we want to put a characteristic for our dynamic system, which is omega. We want to put it in the equation. So we have manipulated this. It's like a small trick here. I put theta over t times t, then theta over t, it is omega, and then times t. So the description of any point on this circle, the projection of it on the vertical axis is going to be described by the radius r and the angular velocity, which is theta dot, the angular velocity, or omega, times t at any point t, which is, or any point of time, which is t, right? So now it is very easy for us to describe this vertical motion of the particle around this circumference. Okay, now let's go, remember Will? Now let's go to give the linear displacement along this axis and linear velocity and linear acceleration. We're going to put it into equations, and by magic you're going to find that we will put the first differential equation for describing the motion of this particle. Okay, now let's go and see. So first of all, just a rule of thumb, I think that you know it very well, whenever that we have like theta here, okay, and this is r, this is the hypotenuse, so the vertical part is going to be r sine theta, the horizontal is going to be r cosine theta, just only to remember it. Okay, now let's say that the linear velocity, so the linear velocity, sorry, the linear displacement, so the linear displacement, the linear displacement, okay, so the linear displacement, sorry, here there is displacement, okay, which is, we are going to call it y. It is going to be y equal to r sine omega t, as we said, right? R sine omega t. And then we are going to, we want to know what is the linear, exactly, velocity. What is the linear velocity? Which is going to be y prime. It is going to be y prime. It equals to what? Exactly the first derivative of y. It is going to be dy by dt. This means that it is going to be r omega, because it is constant as we said, times cosine omega t. The derivation of sine, the derivative of sine, it is cosine. Okay, so this is the linear velocity. Linear velocity here. This is the linear velocity. Here, this is the linear displacement of what? Again, remember well, we are talking about the vertical axis. We are talking about the vertical axis. Okay? Oh, we have... Oh. Okay, so I think that I have lost the data here. So sorry for this. So anyway... Oh, I think that I have lost the data that I have mentioned by just scrolling. Okay, so I think that it's better to use okay, I'm going to use this pen. Okay, so now we are going to say that, sorry, I'm going to again say that it is equal to r sine omega t, and then y dot, which is the velocity, is going to be equal to r omega cosine omega t. Okay, this is linear displacement, this is linear velocity. And then the linear acceleration is going to be, it is the derivative of this one, so it is going to be d to y over d t squared, and it equals to, after derivation, it is going to be minus r omega squared sine omega t. Okay, remember I'm talking about what? If we have this circle, we can draw it quickly here. So if we have the point here, this is the point, the projection that we are talking about is P prime here. This is the projection of this point, and we are talking about theta here. So this projection, the point as if it goes up and down on this vertical projection with linear displacement, linear velocity, linear acceleration, right? So we have like different, okay, we are having like different things, or we are having like different parameters to be used for description of the point on the vertical axis. As we said, the vertical axis is y of t, y of t. Okay, okay. Now I hope that you can understand now. Now look to this equation. Look to this equation here, this one, the last one here. In the left-hand side, we have y double prime, and in the right-hand side, if you look deeper here, minus r omega squared sine omega t, we can put it in, substitute with r sine omega t with y, right? So we can say that y double prime equals to minus omega squared y. Is it right? This is what we are going to have. Then we can put it in a differential equation form, and we can say that it is y double prime plus omega squared y equals to 0, right? So this is what we are going to have here. This is a differential equation. This is a differential equation. A differential equation that we need to understand well. Now, what is the meaning of this differential equation? It means that this is the mathematical form. This is the mathematical form that is going to describe the motion of this point up and down. Okay? So you can imagine that if I say that this is y here, if we say this is the y-axis, the point was here, then it goes here, then it goes here, and so on. So when it goes up, it has y, which is linear displacement, and it has y dot, which is linear velocity, and it has y double dot, which is linear acceleration. So we have like 3 different parameters. Do you remember in the beginning of this video I have mentioned that we need to understand the motion. This is the motion, and here this is the vertical. This is the vertical motion of this particular that we are describing. We are describing b prime, remember, which is or b dash, p dash on the vertical axis. So in order to describe this motion, we are going to use the the basic principles of trigonometry, for example, and we can obtain the displacement, velocity, and acceleration. And then we are going to put from the last equation, we are going to put it in a form of a mathematical form. This mathematical form is going to give us the equation of motion. We call this EOM. EOM. So equation of motion. For what? For this P prime, or the vertical projection of P on the vertical axis. Okay. Now, what and how we can describe this? We call this as, this is a differential equation of motion of P prime along the vertical diameter of the circle with specified initial condition. So it started with initial condition. Remember that our omega, it is constant here. Theta of t, we assume it to be constant. Okay. So now this is the meaning. Now, what is this differential equation? This differential equation mathematically can be solved. So remember we said that understand or describe the motion, if you remember. And after that, like pick the physical law, okay? The physical law. This is the second thing that we have done, okay? And after that, we are having the math, or apply math, which we are doing right now. We are applying math now. We have obtained our equation of motion. This is a differential equation. This differential equation is, we call it differential equation because the relation between the known function with its derivative, which is y with its derivative, and unknown function if it contains coefficient of the unknown function, okay? And this equation also, it is homogeneous. We call it homogeneous equation, okay? This is homogeneous because the right-hand side is 0, okay? And it is ordinary. It is not partial differential equation because it contains only one independent variable. And it is second order because the order of the highest derivative in the equation is 2. We have the second derivative here, and it is first degree, okay? First degree, second order homogeneous differential equation. First degree because the fractional power or radical, which is of y double prime, for example, it is 1 raised to the power 1, so it is first degree. So we have a first degree, second order homogeneous ordinary differential equation which can be solved easily using our mathematical skills, and we can find the solution of this equation. Okay? So we can find the solution of this equation. Okay, so what is the solution of this equation? Let's go to the next. I want to wrap up, but I'm going to finish with this. So the general solution of this equation, of this differential equation that we have described now, our mathematicians or our mathematic friends, they said to us that it can be, this general solution is A sine omega t plus B cosine omega t. This is the general solution of this equation. So are going to ask me what is A and B. Actually, they are like can be obtained from initial condition. They are constants that can be obtained from where? From the initial conditions. Easily, for any problem, we are going to give some initial conditions, and we are able to give values for A and B. Well, can we describe what we have done, this solution? Can we describe it for the linear displacement and linear velocity and linear acceleration? The answer is yes, we can. So we can go here, for example, and I'm going to draw like different axes here. So this is, let's assume that this axis is omega t. Here it is going to be versus, here it is going to be versus y, and then here we're going to make the same. Horizontal axis is omega t, and the vertical, it is going to be y prime, and the last thing, it is going to be same horizontal axis omega t, and the vertical is going to be y double prime. So we need to find the relation between these. So let's change the color here, make it blue, for example, and here. So we are going to like make the relation between the y linear displacement and remember omega t. Okay, for y here it was equal, if you remember, r sine omega t, right? And y prime, it equals to what? R omega sine omega t, right? And y double prime, it was equal, or it equals to minus omega squared y, right? So when we are drawing at the first point here, if we say this is the first at t equal to 0, y equal to r sine omega t, which is 0. So sine 0. This means that it is going to be 0 also. And if we're going to talk about, if we are saying that this is pi over 2, for example, then it would reach the maximum here, right? And it will reach something like this. The maximum here is going to be how much? Exactly r here. And then at pi, if we say this is pi, it would reach to 0, right? Sine pi, it would equal to 0 again, and then we are going to have everything 0. And then at 3 pi over 2, here for example, so at this, which is 3 pi over 2, this means that the maximum, but in the opposite direction, okay, and it is going to be, the value here is going to be minus r, right? And then we are going to end up here, which is going to be 2 pi, right? That's it. This is the graphical representation of it. If we want to like put the same point here for the graphical representation of the y prime and y double prime, then we're going to start with the maximum here. Here at this point, omega t equals to 0. So sine 0 is going to be 1, and r omega would be our case. So this value is going to be r omega, right? And then we're going to have 0 here, and then it is going to be maximum here, 0 here, and then maximum here. So this is our case, okay? And of course, the maximum value here is going to be minus r omega. For y double prime omega t, whenever that it equals to 0, then we're going to find that the opposite here, it is something like this. Here 0 is 0, and then when we have pi over 2, it is going to be, the value here, the maximum is going to be minus r omega squared, right? And then go to 0, because omega t 0 means that this is going to be 0. Remember, y double prime, it equals to minus omega squared y. So y here, it is 0. So this means that omega squared minus omega squared y, it is going to be 0. And here, y, it was equal to minus r, right? So it will be minus r omega squared here with the value. This is the maximum here. It is going to be r omega squared, and then here would be 0. Okay? So I hope that we can understand this. This is what we call it the characteristics of harmonic motion. This is the characteristic, what I have drawn now. We call this the characteristics of the harmonic motion. We understood now how we can describe in a mathematical form and in a graphical form the motion of the particle on this circle that we were talking about using our mathematical modeling that we have obtained using the differential equation that we have obtained, which is this differential equation. This is what we call it the equation of motion. And we found a solution for it. We call this the general solution. Then graphically we could put this general solution, the relation between omega t, the horizontal, and y, which is the linear displacement, y prime, the linear velocity, and y double prime, which is the linear acceleration. And we could put them and understand how the particle is going to behave under each case, and the relation between these graphical representation for displacement, velocity, and acceleration. Okay, this is I think I'm going to stop here for today's lecture, and next time we can continue with other topic. Thank you, and see you for the next class, and I hope the best for you.